All right, let's talk about the most important molecules you've probably never really thought about, alkanes. These are the simple, invisible workhorses that, no joke, power our modern world right from the moment our alarm clocks go off. Seriously, just think about your morning routine. Did you hop in a car? Well, that's gasoline. Make some eggs on a gas stove? That's natural gas. Use a lighter for anything? Butane. See? They're all alkanes, just hiding in plain sight, doing all the heavy lifting for us. So let's start right there with the fuels that are just woven into the fabric of our daily lives. We're going to peel back the layers on the very basic chemistry that makes all of this tick. Now, what's so cool here is how each specific alkane is kind of hand-picked for its job. You've got methane, the simplest of them all, which gets piped right into our homes as natural gas. Propane is a little bigger, making it perfect for those portable tanks on our barbecue grills. Butane, that's what you've got in a lighter. An octane is a major player in that complex cocktail we call gasoline. It's all one family, just with different jobs. So, what is the one thing all these molecules have in common? Well, they share an incredibly simple chemical blueprint. And to really get alkanes, you first have to meet their parent family. And the name pretty much gives the whole game away. Hydrocarbons. They're molecules made of just two things: hydrogen atoms and carbon atoms. That's it. It's this beautiful simplicity that's the foundation for a staggering amount of our world's energy. And within this big hydrocarbon family, alkanes are the simplest of the simple. The carbon atoms are linked together with only single bonds, which are super strong and stable. This structure means they can hold on to the absolute maximum number of hydrogen atoms possible. Chemists have a great word for this. They call them saturated, kind of like a sponge that's soaked up so much water it just can't hold another drop. Okay, so how do we get from methane, the little guy, all the way up to more complex alkanes like octane? Well, the process is way simpler than you'd think. And honestly, the best way to picture it is to think about a toy you definitely played with as a kid. It's really just a simple, elegant system. You start with your first block, methane. That's one carbon with 4 hydrogens. To build the next one, you just click in a standard building block, and then you just keep adding that same piece over and over to make the chain longer. It's an incredibly neat and predictable way to build a whole family of molecules. And you know what? This simple structure leads to a wonderfully simple naming system. The first part of the name tells you how many carbons are in the main chain: meth for 1, F for 2, prop for 3, and so on. And that ane at the end, that's just the family name, telling you it's an alkane. So a 3-carbon chain is propane, an 8-carbon chain, octane. Easy, right? But this is where it gets really interesting. This simple difference in length, just adding more Lego blocks, completely changes the molecule's personality. It dictates everything about how it acts in the real world. Just look at the pattern here. The little guys, the alkanes with just 1 to 4 carbons, they're all gases at room temperature. That's your methane and propane. But as those chains get longer, they become liquids, like gasoline. And if you keep going, making the chains even longer, you start getting waxy solids, like the paraffin wax in candles. It's all about the size. This chart just slams that point home. I mean, to turn methane gas into a liquid, you have to get it incredibly cold, way down to minus 161 degrees Celsius. But propane? It only needs to get to minus 42. You see that clear relationship, right? The bigger the molecule gets, the higher its boiling point goes. So why does that happen? Think of it like Velcro. Small molecules are like tiny little dots of Velcro. They don't have much surface area to stick to each other, so they fly apart really easily. But the longer chains? They're like long strips of Velcro. They can lie right next to each other and get sticky all along their length. It's a weak attraction, but add it all up, and it's significant. To get them to boil and fly apart, you have to pump in a lot more energy, more heat, to rip those connections apart. Another key personality traits: alkanes are totally antisocial when it comes to water. They're what we call nonpolar molecules. Their electrical charge is all balanced out. Water, on the other hand, is polar. It has a slightly positive and negative end. And a basic rule in chemistry is like dissolves like. So nonpolar alkanes and polar water, they want nothing to do with each other. It's the exact same reason oil and vinegar separate in your salad dressing. Okay, so let's recap. We know they're simple chains of carbon and hydrogen. We know they're pretty stable, and they don't mix with water. So what makes them the absolute backbone of our energy world? Well, it all comes down to one incredible chemical talent they have. I mean, on the surface, they don't seem all that reactive, right? They're just these straightforward saturated chains. So what is the one trick they do? The one thing that has literally changed the entire course of human history? That's it. Their superpower is combustion, the ability to burn and to do it cleanly while releasing a massive amount of energy is what makes them so unbelievably useful. See, when you give them a little spark, alkanes react like crazy with the oxygen in the air. This reaction shatters their bonds, rearranges all the atoms, and releases a huge amount of stored chemical energy in the form of heat and light. And in a perfect world, the only things left over are carbon dioxide and water vapor. That blast of energy is what pushes the pistons in your car engine and heats the water for your morning shower. When you really step back and think about it, it's kind of staggering. The entire industrial age was built on the energy we figured out how to unlock from these incredibly simple molecules. So it really makes you wonder, as we look to the future, what other simple blueprints are out there just waiting to be discovered that are going to define our next 100 years? Thanks for tuning in.